I'm now going to walk you through how to use VOXI in exploration for nickel. To do that, I will use geophysical data collected over a property located in the northeast rim of the Sudbury Basin. The Sudbury Basin, located in Ontario, Canada, is a multi-ring deformed impact crater with a lot of associated economic mineralization. The mineralization happens along these rims as well as offset dikes that radiate out of the basin. Let me now show you. In the middle of the map, you will notice the characteristic magnetic signature of the Sudbury Basin with its multiple rings and the offset dikes. This data was downloaded from the GSC website. I'd like to draw your attention to the northeast corner of the basin, the Podolsky property. I will now zoom in. This property is held by KGHM, formerly QuadriFNX. QuadriFNX conducted extensive work on the property. There is lots of drill hole information available, along with geological and geochemical information. As well, QuadriFNX commissioned Sandra Geophysics to fly a gravity airborne survey in this area, as well as a request to fly an EM that had associated MAG. And the map that you see on the screen is the magnetic map. Note that right here we have concurrent gravity high and magnetic high. We know that the nickel ore in the Sudbury Basin has an associated magnetic high. Also, the nickel ore is a very dense rock, so we would expect to see a gravity high. Now, let's go and model this area. To do that, I will go to the VOXI menu. VOXI will appear in your OASIS montage menu bar in the April 2012 release. I will choose the polygon option because I will draw a polygon around the area that I want to model. Also, I will give a unique name to my inversion session. Before I move on, I need to define the digital elevation model. In this particular case, LiDAR was surveyed concurrently with the gravity. However, would I not have had this information, I could go to Seeker and download the digital elevation SRTM model for this area. Note how VOXI has filled in all the other details for me. VOXI is geospatially aware, so it could pick up the coordinate system from the map and also propose a reasonable cell size for the modeling. Note also, I have the mesh size of the area that I will be modeling. Here we go. This is my model. This is the volume for which the susceptibility property will be calculated. I now have to provide the magnetic data that covers this area. I can provide the magnetic data as a database or as a grid. I'll pick my magnetic data, and I also have to define at what elevation it was surveyed. Would I not have any radar elevation information? I can define an average constant elevation, but in this case, we do have the elevation. Since it's magnetic data, we will be modeling susceptibility. Also note how, again, VOXI filled in details for me. All surveys have inherently an associated noise level. Also, we need to know the geomagnetic field at the time of the survey in order to properly calculate the susceptibility model. And lastly, it is not really absolute values of susceptibility that we will be calculating, but rather their variation. So it is prudent to remove the background in order to better resolve the variation in the susceptibility. I now see the magnetic data draped on the elevation at which it was surveyed. I am ready to go. I can go and model the susceptibility property of this volume of earth. All the magic happens right here. I am ready to run the inversion. Would I not have supplied all the necessary information, the run inversion would have been disabled. The fact that I can run it tells me we have all the information we need. Note, we supplied the magnetic data, the datum at which it was surveyed, the elevation model, and we defined the area with a polygon. Those are the only entries that I had to key in. The number of tokens needed to run an inversion is directly proportional to the number of points on the surface of the voxel model. I accept the cost and I move on. First thing that happens is that the data is uploaded to the cloud. Once the data is uploaded, I can actually close my session and have access to the full power of my computer to do other processing. The computer is not locked for the duration of the inversion. The next thing that happens is that the cores in the cloud are initialized to run the inversion. And then we start running the inversion. You can notice that this Earth volume has 161,000 points, and 8 cores have been triggered to run the inversion. While the inversion is going on, I would like to draw your attention to the constraint item on the tree viewer. Would you have a priori knowledge, such as thickness of overburden or any knowledge about the contacts? You can enter them as constraints to better control the results of your inversion. The inversion item on the tree appears when we start running an inversion, and each inversion session gets a unique name compiled with the type of property that we are modeling along with the timestamp when the inversion was triggered. Great, the inversion is done. It started at 10:35 and ended at 10:38. 3 minutes to run an inversion for a voxel model with 161,000 points. I can close the progress log and turn on the susceptibility model. Let's turn off the mesh to better see the results. Note that we were specifically interested in this anomaly right here that had a concurrent mag and gravity response. Let me slice through this model. Right here is where the high susceptibility is concentrated. Although I have a secondary item located right here, I'm not really interested in this high susceptibility area because I know that it doesn't have a concurrent gravity high. I will now clip the data to show only the high susceptibility areas. And here is a look from below. In the interest of time, I also modeled the gravity data and produced a map that has the gravity and the magnetic inversion results along with other a priori structural information that was made available to us by QuadraFNX. Let me minimize this map and open the 3D map with the results. Once again, here is the area where the high susceptibility showed in a lighter shade of magenta and the high density shown in the darker shade of magenta are concentrated. What you see on the lower surface is the terrain. The middle relief surface is the gravity data put on its own relief so that you see the highs very clearly, and the surface above is the magnetic data that is also draped on itself. Let's look what happens in the Earth volume. I will turn off the voxelized high susceptibility areas and show them with isosurfaces. The orange isosurface is actually the high susceptibility, and the green isosurface represents the high density area. Through extensive drill hole information, I have access to the mineralogy. As a result, a nickel ramp model has been built that is displayed in blue. You will notice that the high density and high susceptibility volumes coincide pretty closely with the nickel ore ramp. Let me turn off the drill hole information to better see how these models coincide. I'd like also to point out that we didn't impose any constraints. Would I take advantage of the other information that was made available to us, which is the contacts of the sublayer and the dikes, I can force the inversion to coincide better the high density and high susceptibility volumes. I will zoom in now into the area of interest with the nickel deposit. and rotate the model. This concludes the Voxy demo.